So let's talk about phase coexistence. Phase coexistence and a common tangent construction. Right. Okay, so what's the situation here? We have two phases. We'll just label them 1 and 2. And they can freely exchange components A and B. So two phases, two components. And we know that phase coexistence at equilibrium requires that the Gibbs free energy is stationary. So here's our little picture. We have phase A, as you say, phase 1. Phase 2. And, you know, let's say A is A can be red squares and B can be green circles. And we know that you know, if this boundary is open, then what? Components can freely jump between phases. That's something that can happen. It's an unconstrained internal process. We're not going to stop that from happening. So given that these matter exchanges can happen, how do we determine the equilibrium condition? I'm going to say these fluctuations must leave G stationary at equilibrium. Okay. So this is now zooming in at the molecular level. And I think people understand that, you know, if you have a glass of ice water, there's a boundary between the ice and the water, the liquid water and the solid water. And water molecules will be jumping back and forth between the two phases at that boundary, right, on a molecular length scale and on a molecular time scale. So what does it mean for that process to leave G stationary? That would be our equilibrium condition. So we can get into the math of that. We can say the change of G, now we're going to be at fixed temperature and pressure. So we're not going to worry about that. And we know the total differential of Gibbs free energy from weeks past. It's a sum over components and phases, chemical potential of each component in each phase, times the change in mole number of each component in each phase. So K going, let's see, A, B, these are components. I going 1, 2, these are phases. Okay. So let's write this out, right? This equals mu A 1 d mu dn, sorry. Let me start with mu A1 dn A1 plus mu B1 dN B1 plus mu A2 dN A2 plus mu B2 dN B2. Okay, so we've written that out. Now we're going to use conservation of mass. And conservation of mass tells me that, I can have molecules or atoms jumping back and forth, but I can't have them just disappearing, right? Or just appearing. I've got to have mass conserved. So conservation of mass tells me that dN A1 equals minus dNA2 and dNB1 equals minus dNB2. Okay, so it's two equations, and so we're going to reduce our number of independent variables from 4 to 2. So I'm going to do that, and I get this. Mu A1 minus mu A2 dN A1 plus mu B1 minus mu B2 dN B1. So I have 4 independent variables. I applied 2 constraints. I end up with 2 independent variables. And this has a familiar form for us. These here are the unconstrained independent variables. All right, those are the unconstrained independent variables. And what do we call the multipliers in front of the independent variables in this sort of differential form? What do we call this thing and this thing? All right. This is a differential form for a dependent variable and how it varies with 2 independent variables. And we have...
It's the coefficient.
They're coefficients. Thank you. I didn't notice who that was, but thank you. Right, coefficients. Good. So this is a form that we are familiar with. And we know from when we've solved equilibrium conditions before in this class that dg pt equals 0 requires coefficients to be 0. That's our equilibrium condition. And in this case, what that means, the chemical potential of A is the same in both phases, and the chemical potential of B is the same in both phases. When that happens, phases can exchange mass freely without changing overall Gibbs free energy. Or in other words, Gibbs free energy is stationary. Okay. So the math is the same. There's a lot of pattern recognition that kicks in this class. The math is the same formally as we've seen before. We're just exploring different cases of this. And so, right, chemical potential is the same. So these particles, they can move back and forth They can change their phase, but their chemical potential will remain unchanged. So the overall Gibbs free energy will remain unchanged. Okay. Now, how do we analyze that? Right. In general, each phase has its own solution model and partial molar properties of mixing. So what do I mean by that? Mu A in phase 1 equals mu A in its reference state plus delta mu A of mixing in phase 1. Mu A in phase 2 equals mu A in its reference state plus delta mu A in phase 2 mixing. And I can write the same for the other component. Mu B in phase 1 equals mu B naught plus the change in chemical potential of B due to mixing in phase 1. And chemical potential of B in phase 2 equals the reference state plus the change in chemical potential of B due to mixing phase 2. Why did I write it in this way? I wrote it in this way because we see that these pure components pure component A and pure component B, those terms are the same in this equation as this equation, or they're the same in this equation as this equation. It's the chemical potential of A in its pure state. It's the chemical potential of A in its pure state. It doesn't care what kind of mixture you're going to make out of it. This is sort of like ingredients on the shelf, right? If you got sugar on the shelf, that's pure sugar. Its thermodynamic properties don't care whether you're going to go make cupcakes or you're going to make like syrup out of it, right? It's just pure sugar. So its reference state is unchanged, doesn't depend on what you're about to mix it into. So in words, the reference states are fixed, and the mu k naught don't depend on mixing. The properties of the ingredients don't depend on your recipe. Okay, so if we have mu A1 equals mu A2 as our equilibrium condition, this becomes delta mu A of mixing 1 equals delta mu A of mixing 2. And similarly, mu B1 equals mu B2 delta mu B of mixing 1 equals delta mu B of mixing 2. And these are our two-phase coexistence equilibrium conditions. Those are our equilibrium conditions. So now we're going to use something which we introduced maybe a week or more ago, which is the graphical solution for partial molar properties. And let me remind you what that was. We had now specific to the case of Gibbs, because that's pretty much the only way we're going to be using this. In O2O, we had here Gibbs free energy. And we had this concept of a solution model. So let me just draw a section of a solution model. Draw the whole thing because I don't need the whole thing. And let's imagine some system composition here. That'll be X2. That's X2. The way that we found the partial molar Gibbs free energy of mixing was we drew the tangent to the solution model at that composition. And the intercepts were the partial molar properties of mixing. So this intercept here is mu2 at X2. And this intercept here is mu1 at X1. Right, so I hope you do remember this. If you don't, just rewind for a couple of lectures. So we had this graphical solution. Now we introduced this for one solution model. So what we're going to do now is use this tangent construction for the case of two different phases. This becomes a common tangent construction. It's called, or if you like, you could just call it a condition for two-phase equilibrium. So how does that look? Well, let's draw one phase. There's part of a solution model for one phase. Let's draw another phase. There's part of a solution model for another phase. And now I'm going to look for a common tangent. Let's say that I drew that accurately, and we have a tangent which is common to both curves. This is phase 1. This is phase 2. Let's say, now using our notation from the previous slides, let's say this is composition of component B and phase 1. This is composition of component B in phase 2. These intercepts are the chemical potentials B and A. So what we've shown is a common tangent which is satisfied at compositions XB1 and XB2. Right, it's only satisfied at these compositions. If you look at these curves, the way I've drawn them, there's no other common tangent. It's only those two particular compositions. And for those two particular compositions, common tangent satisfy the composition, right? That ensures that the chemical potential mu A1 equals mu A2, mu B1 equals mu B2. All right, this is the equilibrium condition. Right. So a common tangent on a free energy composition diagram is the same as the equilibrium condition. When you can draw the common tangent, then you can have two-phase equilibrium. And only at those compositions that satisfy the common tangent. If there's no common tangent you can draw, then there's no two-phase equilibrium possible. Right, okay. So we're sort of knitting things together here across different lectures. Okay, I'm going to spend the rest of the class on how this works in the case of spinodal systems. So before I make it a little bit more specific to spinodal systems, are there any questions on the concept or on the math of this so far? Okay. So let's move on then. Okay, so now we're going to make this a little more specific. We're going to talk about an example of common tangent construction. And that is spinodal systems. So something a little bit familiar to us. Right, so here's a general view of a free energy composition diagram for a spinodal system. This is going to be delta G of mixing. And let's draw a solution model for a phase that exhibits spinodal decomposition. So let's draw something like that. Works. You've been playing with stuff, something like this in P-sets and in previous lectures. And so this has a common tangent. Let me draw it. Okay, so it has a common tangent, let's say here, and let's say here. Just eyeballing this, obviously. And so let's note the composition of the system when it satisfies common tangent. Let's say we have X, B, we'll call that phase 1, X, B, we'll call that phase 2. The zero of the free energy mixing is there. And these intercepts are delta mu B of mixing and delta mu A of mixing. Okay, and so what's happened in this system? What happens at equilibrium? This system has phase separated. It has spontaneously unmixed into two different phases with what? These two compositions. So you could say this is a composition rich in component A. Right, so that composition we're A rich. And here's a composition rich in component And we saw some examples of this on the slides from from Monday's lecture. Okay, so there's the common tangent construction for a spinodal system. Okay. When the common tangent is possible, the free energy of two-phase system is lower than that of fully mixed one-phase system. As you would expect for equilibrium, it's got the lowest free energy. I'm not going to prove this to you right now, but I'm going to show you graphically how it comes about. Here again is a free energy composition diagram. And let me say my solution model looks kind of like this. A little bit ugly here. Let's say it looks like that. And here's my common tangent, points of tangency, and my compositions here at those points of common tangency. And let's imagine an overall system composition here. Let's imagine an overall system composition there. It can be shown that relative to a fully mixed system, the free energy can be decreased by exactly this amount by splitting into two different phases. So spontaneous unmixing lowers the free energy by exactly the amount that I drew here on the plot. So the single phase, the Gibbs free energy of the single phase system equals the Gibbs free energy of the components in their pure state, plus just the value of this curve evaluated at the overall composition, plus delta G mix evaluated at overall XB. And two-phase, the Gibbs free energy is, again, the Gibbs free energy of the components unmixed, plus the Gibbs free energy of each of those two phases. Sorry. Right. Okay. So single phase, it's just the reference state plus the evaluation of this solution model at that composition. Two phases, it's the reference state plus the evaluation of this solution model at these two compositions weighted by the phase fractions. So this here is solution model. Solution model. This is solution model. And these are phase fractions. Okay. So you're working some of these concepts on the problem set. All right, so now we're going to continue exploring the spinodal case, right? The common tangents. They define the tie lines on a binary phase diagram. Right, so again, for the example of spinodal system, example of a spinodal system, here I'll draw a phase diagram. We have temperature, composition, and we have a region of spontaneous, or I should say region of phase separation, right? And let's see, we have the highest temperature here, which is sometimes marked as U star, or different notations there. I'll just say T star. And we have these tie lines, right? These tie lines define the compositions that can coexist at equilibrium with each other. So in a system like this, mixing favored a high temp, right? In fact, it's fully miscible at high temp, right? At low temp, the system spontaneously unmixes. Spontaneously unmixes. And the tie lines that are drawn in the two-phase region connect compositions that coexist at equilibrium. And so this is a reminder basically of what tie lines are. How do the common tangents define the tie lines? They do it through the free energy composition diagrams. The phase diagram emerges from temp dependence of free energy composition diagrams. So I'm going to draw some snapshots here of how that happens, and then we're going to spend a lot of time in the next couple of weeks on this. So let's say at low temp T1, let me draw a free energy composition diagram for this spinodal system at low temperature. At low temperature T1, delta G of mixing is basically positive, right? That's why we have, let me draw it like this. Right, this is an example. It could look like this. This system has a common tangent, right? So now, right below this, we're going to draw the phase diagram. This is going to be temperature. I'm going to drop down those compositions. This is X, B. And what I've just learned from this common tangent is that these two compositions can coexist at equilibrium at temperature T1. So those are 2 points on the phase diagram. And I know what's going to happen if I vary temperature. So I'm just going to draw those as 2 points on little line segments, and I'm going to connect them with a tie line. Okay. What about medium temp? What about medium temp? So as I raise the temperature, my free energy composition diagram will change. As I raise the temperature, mixing becomes more favored. So now my 0 of delta G of mixing will be there, and I'll draw it maybe like this. Okay, I've got a common tangent, right? There and there. Let's draw the corresponding phase diagram. And this is X, B. Right. At T1, I had coexistence at, let's say, here and here, being a little bit rough with that, right? So we had a tie line here. Now at T2, I've got coexistence let's say this is T2. Let's say my coexistence is here and here. Right? I'm calling this T2. And I've got a tie line there. And now I'm only drawing discrete points of temperature, but you can imagine this sort of now starts to define a family of tie lines. So I've shown you how the tie lines at T1 and T2 emerge, but you can imagine that as I sweep the temperature, I have a family of tie lines, and this starts to sweep out the two-phase region. And then at high temp, T3, let's do it again. At high temp, I know that my free energy mixing will pretty much be strictly negative. So I'm going to draw the 0 way up there. And I can say my solution model might look like that. So no common tangents, no inflection points, strictly positive curvature throughout. And so that section of my phase diagram will show full miscibility. Here's XB. Here's T1. Here's T2. And let's say this up here is T3. And I'm just going to sketch this now. Let's see, we have right. So now my region of two-phase region has closed. And I have finished drawing my spinodal phase diagram. Right. So the way that I did this here is I did a very, very slow motion animation for you, right? At each temperature, you have a free energy composition diagram. At each temperature, that free energy composition diagram determines for you whether or not there are any tie lines in the phase diagram. It tells you about the phase stability and equilibrium as a function of composition at that temperature. And so as you tune the temperature as a knob, you sweep through a series of free energy composition diagrams. And you gradually build up the phase diagram. So you can imagine a flipbook style version of this. The textbook has some nice examples of this, of these free energy composition diagrams giving rise to phase diagrams. These sort of single temperature snapshots. And in the weeks ahead, we're also going to play with an online kind of animated version of this, which we've coded up for use in this class. Okay, that's where I want to leave it for today. We're finishing about 5 minutes early, so we have plenty of time for questions. I just saw there was a chat. Does a common tangent construction help us to say anything about the kinetics of the process of segregation? No, it doesn't. This doesn't tell us anything about kinetics. So this tells us about the equilibrium. The common tangent construction tells us about the equilibrium configuration of the system. Now, we can infer a lot of things about kinetics from the phase diagrams. And we can also infer things about kinetics from the driving force for phase segregation. That goes beyond the scope of the class, but kinetics is really interesting, and it starts from this point. Kinetic studies start from phase diagrams like this, and a tendency of a system to spontaneously unmix. That is a tendency for pattern formation. And what patterns actually form depends on the kinetics, depends on diffusion coefficients, depends on temperature. And that's kind of where this curriculum takes off in the fall.